The system in general classify as first order and second order. So here we are going to start with first order, and here we'll understand the meaning of first order. First order means the denominator of the transfer function is first order equation, or I can say the transfer function of the system has only one pole, not more than one pole only. If the transfer function has one pole, we consider it as a first order system. How am I going to deal with it, and what is the meaning of dealing with it? What is the meaning of analysis? That's what we are going to see here. First, let us agree that the pole is going to be located at this point, and since it's pole, we put it as a x. And we know that the input in general, if I study it from step input, is going to be as a 1 over s, similar to the previous example. So if I want to go to the time domain, if I want to convert in time domain, we are going to find that it's equal to Cf of t, as I show you in the previous slide, which the force response we call it, plus the Cn of t, which is the natural response, which found here as 1 minus exponential of minus at. To understand what is this, or to figure out what is this, let us plot it. How to plot it? We will change the value of t and plot. Change the value of t and plot, and evaluate the points on S-plan. What is the response, or how the response is going to look like? We will see this in the next slide. So here is the response. When we plot the function shown earlier, we will find that the function is going to be the blue one, the blue color here, which means all the first order responses going to have the same shape, exactly same shape. Then what is the difference between one and the other? The difference will be in terms of times. Like, for example, until I reach to this point, is the time for certain function same as the time for the other function? Or until I reach to this point, is the time taken from function to function is same? I mean this time, or this time, or this time. Are these times going to be the same? Actually, what will decide these times is the location of the pole, the value of the pole. I mean, the value of the pole will decide on these locations. For that, we are going to give definition to each of these points. We will give definition to make us clear. So the difference between function to other function in the first order is the definitions which we are going to see in the next slide. So these are the definition which are going to make difference between function and the other. We will start by time constant. Time constant is the time for the exponential to decay to 37% of the initial value, or the time the time for the step response to rise to 63% of the final value. What he mean by this? Let us look at the second one, because the second one is valid for our response here. So if I look at the second one, the response is going from beginning up to the final value. This is the final value, which is going to be 1. So where is 63%? This is 60%. This is 63%. So the time taken for the response to reach to this point is going to be this time. So this time we call it time constant, Tc. The time taken to go from the beginning up to 63% of the response. We call it time constant. And it's evaluated from the transfer function as 1 over a. It's translated or calculated, can be calculated from the transfer function as a 1 over the pole. So 1 over the pole is equal to Tc. Remember, there is very simple derivation for this equation, but I found that it's better to put it direct because the equation is simple to derive. For that, I put it direct. How about time rise, which is the second one? Time rise also will make difference between one response to the other response. Time rise is the time taken by the function to go from 1% of the response to 90% of the response. That time we call it time rise. So what is 1%? You see, this is the response, the final response. We said 1. That means starting from 0.1, which 1%, or sorry, 10%, not 1%. and it's going to go up to 90%. The time between them here, this time, is known as time rise. Okay, so the time rise is the time to go from 10% to 90%, and it's to be calculated as 2.2 over the pole, 2.2 over A, where A is the pole. Now let's go to TS. TS is the settling time, where the settling time is the time needed for the response to go or to oscillate within 2% of the final value. What does it mean? The final value is this. So I will go to, this is 100%. I will go to 98%. So this is a 98% somewhere here. Somewhere here. So the time taken from the beginning until I go to 98% of the response, we call it settling time. Settling time means the response will settle at certain point. Means it's going to go to the steady state region. It's going to enter the steady state region. For that we said, I'm going again one more time, the time taken until the response go to plus or minus 2% of the final value. That means this is 1, here it's 1, here is 9, means 0.98, 0.98, and go straight up to this point here, which means this is the time which known to us as a settling time, where the response finish going to go to the value within plus minus 2% of the final value. Why we are saying plus minus 2%? Because this response will not be always a straight line. It will oscillate sometimes, oscillate. So if it's oscillating within 2%, it's going to be fine. We can consider this time as the settling time. And it's to be calculated as a 1 over the pole value. Examples are very simple, direct application. So he gave me a function where this function is having its pole is 50. The denominator is s plus 50, which means the pole equal to minus 50. That means A equal to minus 50. A equal to 50, sorry. The pole is minus 50. Pole is minus 50. A is equal to 50. So when we will calculate, TS is 1 over A, 1 over 50 equal to this much. TS equal to 0.08. TR equal to 0.04. So if the pole, for example, is 40 or 10 or 100 or 500, they are going to give us different times here. Different time. This time, and this time will be different. So that's how we can evaluate the first order system. Now in second order system is going to be if the denominator of the transfer function is second order equation, like here. If you look here, this is the denominator and it's second order equation. If it's second order equation, we will call the system a second order system. In second order system, we have variety of response. We will study them as we are going in the next slides. Remember, in the first order, the response used to be always like this. Is second order give us the same response or not? That's what we need to know. And how we evaluate the location or the times, the definition, how we evaluate the definition of the first order. It's by the pole. We have only one pole, and from that pole we could evaluate or analyze the system. How about second order? Is it the same? That's what we are going to see in the coming slides. All the second order responses are decided by the second order equation available on the transfer function. I mean this equation. So the pole which will be decided by the equation, the pole location which decided by the equation will decide the type of response. So let us start by overdamp. In overdamp, when we are having this kind of response, so if we look at the second order equation, it's s squared plus 9s plus 9. When we multiply it into the input, we are going to get C of s, which is seen here. So from there, we are going to find in the partial fraction expansion, when we evaluate it, we will find that the system has two poles, one of them, or three poles, sorry, one coming from the force response, and one will be located at minus 7.8 and the other at minus 1.14. If we try to get the response in time domain, we will find that is equal to k1 from here plus k2 exponential of the first pole t, I mean minus the first pole t, plus the other one, where both of these two are the natural response. If we try to plot that function, the function shown in the previous slide, you will find that this is how it looked like. Now we can decide from the location of the pole on how the response will going to look like. So he's saying here, if we have the two poles located at S-plan, at the real axis of S-plan, the two pole located at the real axis of S-plan, we are going to call the system overdamped. And its response is similar to what you can see here. And its time response, or the equation, can be evaluated as you see here. So that's the overdamped. So overdamped means the pole located at the real axis of S-plan, and the response usually look like this. Underdamped, now I think we figure out the things. The location of the pole will decide on something. The location of the pole will decide on the type of the response. So here we have underdamped response. The system here looks the same, but what is different as compared to the previous one is the location of the pole. Let's go to the natural response here. Sorry, to the response. In the response, we find in S domain is as you see here, and we try to convert it. We find that the poles are complex. The poles are complex. So the pole has real value and imaginary value, which means it's complex. So from there we can calculate K1, K2, and K3, and then substitute to get the response. Where the response, I think we figure it out when we calculate or when we evaluate the Laplace, or when we study the Laplace. It's equal to K1, which is the constant K1, plus exponential t into K2 cosine root 8 t plus K3 sine root 8 into t. Like what you can see here for the function we are having. For this function, if we calculate its response, is going to be as you can see here. Now let us plot it to see how it's going to look like. And in the second slide, we will see the response shape, how it look like, and the location of the pole. So notice here, the location of the pole, as I explained earlier, as I explained in the previous slide, the pole is having real value and imaginary value, which means it's a complex quantity, and this is complex quantity. And the response, as you see here, the response is having this format. Even this format needs some definitions to analyze it. We cannot just look at it as this shape. There are some definitions will make us clearer about this one. But for the time being, I know that this is the shape of the underdamped. Let us go through these observations before we go to the definition of the parts of the response given earlier. He said the real part of the pole matches the exponential decay frequency of the sinusoidal amplitude. That's the first observation. The second one, he said the imaginary part, because I said the poles having real part and imaginary part. The imaginary part matches the frequency of the sinusoidal oscillation. So the real will talk about exponential decay. Real part, the exponential decay. The imaginary part talking about the frequency of the sinusoidal response. The time constant is equal to the exponential of the real part of the system pole. Okay, the complex pole is equal to sigma plus j omega d. As I told you, we are going to go to the definition. We will see this one after a while. We will see this one. We will see the definition out how to calculate each of these parts. Omega d is the damping frequency of the oscillation. So each of these parts are to be discussed after a while as a definition. The natural response of the this kind of responses is always like this: Cn of t equal to exponential of sigma t into a, or k1, it depends on the constant how you want it to be, cosine of omega d into t plus b sine omega d into t. That's the response shown in the previous slide. But this is in general. Sometimes you can write the equation, the time response, without doing calculation. Without doing the calculation, you can directly go, except you need to calculate A and B. But most of the time, he will ask you to evaluate Cn, I mean the response without the constants. Means keep the constants as unknown and write the equation, so you can write it in this format. Example, by inspection, you see, this is what I mean. This is what I mean. By inspection, write the form of a step response of the system shown. By inspection means you don't calculate, don't evaluate, just direct, you can put them. So what are you in need for here? You need to calculate the value of S from this one. Of course, by calculator, you can calculate it, takes no time. By calculator, you can calculate S, which equal to minus 5 plus minus J 13.25, where sigma is the 5 and omega D is the 13.25. Now, from the equation shown earlier, you can substitute. So the equation going to look like K1, always K1, not calculated because he didn't ask me to calculate. He asked me by inspection. So we don't need to calculate the value of K1. K1 plus exponential of minus 5t into K2 cosine of 13.2, which omega D into t, plus K3 omega d into t, sine omega t into t, which 13.2 t. That's how we can calculate it direct. So when you get this kind of system, the first thing you will do is find S, then you know this format, you can just substitute the value of sigma and omega d. Undamped, and undamped, as you see here, the denominator is second order equation, which equal to S squared plus 9. If you think of it, you will find that S is imaginary, there is no real. S is imaginary. So if you look at the location of the pole for this system, you will find that there are two poles, one at J3, one at minus J3. So that's why we call it undamped. How the system going to look like here? The system going to look like continuously oscillation, or there is continuous oscillation in the response. It will not stop. That's why we call it undamped. There is no damping in it. Because if you remember just now, I said the real quantity of S is going to be in charge or going to affect the damping. But here there is no real, only imaginary. So the system will oscillate all the time. The general format of the response is similar to the previous one. It's similar to the previous one, as you see here. Critically damped, we are having the same thing, second order equation, and in the critically damped, you will find that there are two poles located at the same point. If you notice here, this is the new elements. So when we analyze the system, you will find that there are two poles at S3 here in the interpretation, but I mean in the analysis, if you remember when we discuss the real and repeated function, real and repeated, so we do it in this way. But when I look at the response, this is the response. So this is the one coming from the input, and from the response we are having S plus 3 square, which means there are two poles at 3. I mean, it's going to be seen in the next slide, but in general, if this is minus 3, you will find that there is one pole here and another pole in the top of it. Okay, if the case is like this, we will have what is called the critically damped. This is the general format for it, which is similar to the first case. K1 plus K2 exponential of minus 3t plus K3 t exponential of minus 3t. In a critical damp, as I mentioned, when the two poles located at the same point, we call the system as a critical damp. And if we plot the response, this response, you are going to have this shape. Now we can say, we notice something here, that whenever the poles are real and repeated, when it's real and repeated, you remember, when real and repeated, that means we are having two poles in the same location. We call the response as a critical damp. So that's all for the second order. In the next lecture, we are going to go to more detail about the second order, where we are going to study the detail of the undamped. Undamped is the mostly occur kind of system. So for that, we are going to study it in more detail. I hope everything is clear. Thank you very much.